All right, so with regards to normalization, as I mentioned earlier, the way you have been designing your databases, or hopefully the way you've been designing your databases from the way you were taught, without even realizing, you are designing your database in such a way that it ends up in a stable, normalized state, if I can put it that way. So what you want to do is you want to ensure that when you design your database, you don't have any data that is duplicated in various tables, because that means that you've got to go and update the same data in more than one place. And then that leads us to having those data integrity problems, data duplication, which then leads to having add, change, and delete problems. Okay, so the normalization is a way that you can ensure that you don't have those kind of problems in your database. So we do need to, before we understand the sort of technical stuff about normalization, we've got to go through a couple of definitions, and it's stuff that's been happening, although I haven't given you a formal name to it. Okay, sorry. So if you're going to have a look at the functional dependency, oopsie, no, Cheryl. Okay. So we have a term called functional dependency. So functional dependency, and abbreviated to FD, is a relationship between two attributes, typically between the primary key. Okay, so if the primary key is only one attribute, that's fine, but remember sometimes your primary key could be composite, made up of more than one attribute. Okay, so there's a relationship then between the primary key and other non-primary key attributes within a table, the same table. So in other words, if we say that one column B of a relation is function dependent on another column, so that's like highfalutin description. So let's have a look at if we had a project table and we had an employee table. In our project table, we've got project number and we've got project name. Project number in this table is the primary key, and we're going to say that to find the name of a project, we need to know the project number. So the project name is functionally determined on, or not determined, but functionally dependent on the project number. I'm going to get one name dependent on the number that is entered. So project name is the attribute that is then functionally dependent on project number. If we have a look at the employee table, which has attributes emp number, first name, surname, and a cell number, emp number is the primary key, and then to go and find the first name, we need to know the employee number. To go and find a surname, one surname, we need to know the employee number. To go and find a specific cell number for the employee, we need to know the employee number. So that means first name is functionally dependent on the employee number. To find one value for each of these attributes depends functionally on the value that's entered in the primary key. So to go and sort of write it out a little bit more visually for you, I've said to you that project name is functionally dependent on the project number. And then we would also say, reading it from the primary key point of view, we're going to say the project number attribute will functionally determine the value we see in the project name attribute. So if we enter project number 10, we're going to see the appropriate name for project number 10. So project number 10 functionally determines what value gets shown for project name. And the value that gets shown here dependent on what value was entered for the project number. So that's to try and indicate visually what happens with functional dependency. So project number basically is uniquely identifying one project number, one value in your primary key goes and retrieves one and only one record. In other words, values for all the attributes in that specific record. When we write it out in relational terms, so we don't go and say project number functionally determines project name. What we do is we replace these words with an arrow. So we can say proj number, the value that's entered there will then functionally determine the value that is seen in the project name attribute. So this little phrase here, project number, right arrow, project name, reads proj number functionally determines proj name. And then the determinant, the attribute to specify on the left hand side, remember this is actually your primary key or key. No, let's not say a key, it's an attribute that can be used to uniquely identify, is known as the determinant. The value in here determines the value of the other attributes, and any of the attributes you specify to the right of the arrow is known as a dependent. So the value in here depends on what value is in the project number field. So we have, remember, double D, and I'm not talking about bra sizes now. Okay, so functional dependency, you've got an attribute will functionally determine the value of another attribute, and the attribute that functionally determines is typically the key because it uniquely identifies the values in the dependence. Determinant is placed on the left-hand side of the arrow, dependence placed on the right-hand side of the arrow. Going to our employee table. So we knew our empno was the primary key. So the value in empno will go and functionally determine the first name. So I would draw in my arrow there. If I know the emp number, I would find one surname. If I know the emp number, I would find one cell number. So empno functionally determines the first name, functionally determines surname, and also functionally determines the cell number. So that's writing it out in words, and that's if we do it with our shorthand with the arrow. And remember, this is then the determinant, and these are the dependents. So you'll see that the determinant is a key, and the dependents are simply attributes, okay? And then if we read it in the opposite direction, this way it was saying functionally determines, and if we read it from the attribute side, we're going to say cell number is functionally dependent on employee number. So the value in here depends on what value is in the emp number or in the determinant field. I just need to stop here to see if there are any questions. Okay. Sorry to do this. I just want to see if there are any questions here in the chat. Oh, you don't think I'm recording? No, it is recording. Okay. Any questions so far? Okay, so we look at this example. In this example, we've got a table that is about for a car hire company, and it is basically the car rental table, and it keeps track of the kinds of cars that they have, the individual cars, what make and model they are, and typically how much they charge per day and what the rate is per, they say mileage, but we actually the kilometer rate basically. So the company's decided that the mileage charge, so we've got each car that is on their books, and registration number uniquely identifies each record in this table or each row. So a register number will never be duplicated. It is unique. So we also need to look and see that the company has indicated that the mileage charge is dependent on the engine size. So apart from the fact that if we know the registration number, we can go and determine the make. So we will see for register 111, it is a Ford, and it is a Ford Figo, and it is a 1400, and its daily rentals 15 Rand and 10 Rand per mile or kilometer. And we would see then for registration 222, it's also a Ford, but it's a Mondio, engine size is 1600, 20 Rand per day, 15 Rand per mile or kilometer. So registration number functionally determines make, registration number functionally determines the model, registration number functionally determines the engine size, functionally determines the daily rental amount, and functionally determines the mileage amount. But at the same time, our user has told us that the engine size will depend on the mileage, well, the mileage charge depends on the engine size. So if we go and look at some of the sample data here, we'll see that if the engine size is 1400, the mileage charge was 10. Here's another engine size, 1400, mileage charge is 10. 1400, mileage charge is 10. So in other words, if we know the engine size, we can go functionally determine the mileage charge. 1600 determines to 15 Rand, 1600 yeah, 15 Rand. So now I've just done it in a different color so it can stand out. So in other words, if we know the engine size, we can go functionally determine the mileage charge. And that mileage charge is the same irrespective in the records here. And if we read it in the other direction from the attribute side, remember that the mileage charge is dependent on or functionally dependent on the registration number. The daily rental functionally dependent on the register number. So that is our table overall, but within that we've also now got another functional dependency that we've identified, and that is that engine size determines the mileage charge. So we've got a functional dependency happening inside a bigger functional dependency within another table. So just before we continue, if we look at our tables, the way they have been designed, our entities table, you know, different terminology, same basic thing. Each row within that table contains data about an entity. So if we had our car rental about the cars, each row in that table was for a specific car. Registration 111, registration 222, all different cars that this car rental company owns. Each row about a specific entity or record or an instance. Each column corresponds to the various attributes. So we had a registration number, we had a make, we had a model, we had an engine size, we had a daily rate, and we had a mileage rate. Okay, so each column corresponds to an attribute. Each cell has to be atomic. In other words, we can only store one value in each cell, can only hold a single value. And all entries of a column, so in other words, all attributes have to be the same data type. So it is, if it's a string, all the attributes within that column must have the same data type. If it was a real or a double, all values would then be of the same data type. Each column has a unique name. Okay, so we don't duplicate attribute names. The order of the columns is unimportant. I always put the primary key first. It certainly doesn't make any difference if I took that primary key and moved it from the first, be in the first column, and I put it at the end there. It wouldn't take and change the meaning or the data within any of those rows. So the order of the columns can be swapped around and the data is actually still the same data in that row. Order is different, but it's still the same data. Then also the order of the rows is also unimportant. So the registration 111 happens to be the first record. It doesn't matter if it ended up being in the middle. Okay, so it doesn't change the logic of anything or the meaning of the data in any way if I actually had to move a row and place it somewhere else in the table. And then obviously, very importantly, no two rows may be identical. So in other words, you can't have duplicate data appearing in the table. And about duplicate, I mean all the same data duplicated in another row. So you can't have rows that are duplicated. So those are the characteristics that you need to make sure are applied to when you design an entity or you design a table in your database. So we've spoken about functional dependency. We've spoken about determinants. We've spoken about dependence. We've looked at the characteristics about the table, and now that can lead us on to talking about what we call data normalization. So basically what normalization is, it's simply a process that you can make use of to ensure that your data is organized in such a way that it is not duplicate, doesn't contain any duplication. There's no problems with adding and changing and deleting stuff, so that your data is organized efficiently within your database. So the goal of normalization is we want to get rid of data redundancy. Data redundancy is just a fancy term for duplication of data. We want to make sure that no data is duplicated in different tables, because that means we've got to go to 2 places to change the data, and it would mean, or even duplicated within a table, because it means we've then got to go to several places to change the same value. And it's easy then to make mistakes, and your data is then not consistent and correct, etc. So that can cause problems, and that we also want to make sure that the data dependencies make sense. In other words, the attributes that you put in the table are dependent on that primary key and only that primary key. We don't want to include data where there are extra functional dependencies within that table. We rather want to take it out and put it into its own table. So by having your data normalized, and by that I mean data within each table, if the data in each table is normalized, it means that we can avoid those anomalies where we had problems inserting, deleting, and updating any data in a table. So the basic definition of normalization, for a table to be normalized, this approach was developed by a chap called Codd, and it was expanded, this concept was expanded on by another person called Boyce, but originally it was Codd, and he basically says that for a table to be normalized, every attribute in that table must depend on the key, the whole key, and nothing but the key. So you can't have any kind of functional dependencies within the table, like we had with that car rental example that we had. If that kind of thing happens, we've got to relook at our table, because we've got to do things, we've got to make changes and remove those functional dependencies, so that we have a data in such a way that in the table every attribute depends on that key, the whole key, and nothing but that key. Okay, and you know, this is what I promise to tell the truth, the whole truth, and nothing but the truth. It's that kind of premise that is being followed.